if you drop off of like 5 and 5, it hurts. 5 feet. Okay, the people. Like without so yeah, everyone has like this and then one way relation. I think that's the biggest sort of not while I'm coming off I landed hopefully like slam my shoe like just played it like that. If he's landing like in the middle of the house. This song is it's like oh yeah, it's like
Alrighty, so it is 5:30. I am going to get started. We do have only, including this lecture, we only have 4 lectures left. I'm not sure whether it's a good or a bad thing. That is yet to be determined. But what I do want to do is to make sure that all the concepts that we have introduced so far are covered. I know the homework assignments seem to be important, okay, and they are, okay. But if you cannot finish the homework assignment, it is really not the end of the world because all the homework assignments, all the labs, they only add up to 20% of your final score. What is important that you put in the time to try to get it done. Because the more time you try to get it done, the more time you spend to debug your program, before you starting to understand how things are organized on the stack. Okay, so when I talk about the solution, then things will sink in, and that hopefully will be translating to understanding the material to the point that you can apply that when you are in the final exam, because the final exam is 40%. It's twice of all the points from all the labs and all the homework assignments. So that is important, okay? So putting enough time and effort into the programming assignments is important. And then when I talk about the solution, that is important as well. So this way you can relate, all those concepts and go like, oh, okay, I must be just missing this part, and that's why my program was not working. So anyway, I'm going to get started with the announcement because I do want to make sure that people are aware that there are these announcements. So the first announcement is the starter code of Fibonacci. So this is basically my code that I gave you guys, to get it started. Fibonacci is not due today; it is due on Thursdays. Is that correct? Yes. Okay. So you still got some time. So for those of you who have been trying to figure out how to get it started because you did not read the announcement, here it is. Okay. So this is the source code that you can use to start the entire thing. It includes the main, it includes the entry point of function f, and you just have to kind of define function f in this case. So this is the first one. It is important if you don't know it already. The second one is really important. Okay, so this one is really important because it gives you a link to a module that I just recently wrote. I mean, I wrote this module specifically to help you with the Fibonacci homework assignment. So the way it works is you don't want to do this in one single session. Okay, it is unrealistic for most of you. I would say some of you can probably do it, but it is unrealistic for everybody to say, "Oh, I'm just going to sit down and I'll knock this code out in 2 or 3 hours." Okay, I would say that is actually unrealistic. So you want to approach it in an incremental way. And this particular module talks about how to do it in an incremental way. So I will talk about this a little bit, just because I think it is important to know how to approach a problem, even though the context is in CISP310 with TTPSM and so on and so forth. This is how I would approach writing a program. Whenever there's something complex that I need to do, I will break it down and do it step by step, incrementally, and I will be able to check, whether did I get this part done? Yes, okay, I can confirm that. And then I add some more code and go like, can I get that part done too? Yes, I can confirm that. So I will have multiple points where I can confirm it's like, okay, I got this, I got this. So that this way, whenever I need to get the next part done, I'll be introducing a limited number of lines of code as opposed to, oh, here's the entire program, 100 and something lines, and it doesn't work. Where do I start to debug it, right? So that is what I want to kind of present to you. All right, so the first thing is this code, okay, this is what I want to do, which is basically just implementing the summation of I going from 0 to n. And that's basically the sigma or the summation I want to do. And I'm doing it in a recursive fashion, even though it doesn't have to be done in a recursive way. The reason why I do this recursively because I want to make this a little bit resembling, for example, the Fibonacci program that you guys are trying to do. Okay, so this way, this is a parallel to what you need to do. So I'm showing some steps for this simpler problem, but you can basically apply the same technique to the problem that you are trying to solve. Do we have any questions about the sigma notation, which is all the way up here, or the C code that is corresponding to the sigma notation? And when I'm asking, are there any questions? I'm only asking, are there any format questions, syntax question, and not so much the dynamic behavior of your function app. So are we good so far? Okay. All right, so I'm not seeing any questions. For those of you who are attending remotely, which is, I think, about half the class now, you can also ask questions, but I am not going to read the chat channel. So you will need to use your voice to ask questions. So I just want to make that clear. All right. So what do we do? Now, with this code, you can put it into the C compiler and compile the program and make it run. The problem is, it is a single statement, which means you can only put a single breakpoint within function f, which makes it really difficult to figure out. So when are we calling the first one? When are we calling the second time? When are we not calling? Because it doesn't give you the option of let's evaluate just the condition. And then we proceed to either the then expression or the else expression. It doesn't give you that option. It is one single expression in a single statement. Yes.
Can I ask a small question about the actual assembly code for this?
No, I can only answer big questions.
All right.
Go ahead. Go ahead.
So we specify one value to test it. Does it matter what value that is?
You want it to be smaller. So the chances are, okay, that's covered also, in either the announcement or in this module. Okay. So you want to test it with 0 and 1 first, because those are the non-recursive cases.
I'm going to say for submitting it doesn't matter.
For submitting, it does not matter. Okay. Yeah. But for testing, you want to do it incrementally. So this way you can isolate, if it doesn't work, you can isolate why it is not working. All right, so the first thing you want to do if you want to really understand the C code, and this is beyond the scope of this class, because this has to do with understanding C code and also, how do you turn a program into a form that is easier to debug, okay? But I'm going to cover it because, you might find this technique useful for doing this particular homework assignment. And also possibly in the future, if you have something that looks like this, you might be able to apply the same technique as well. So what we want to do is to turn this code into this code here. In other words, we turn something that is really kind of terse, but concise, okay? It is very to the point, gets the job done and nothing else. And we want to turn it into something that is verbose, which means, oh, okay, it gets the same thing done, but it's using so many more lines and some of these things are not necessary. That is true, but in the process of doing that, we are breaking this code, the original code, into many different statements. We are talking about here's one breakpoint, another one, another one, another one, another one. So now we have multiple places where you can put a breakpoint, or if you just want to do a single step trace, there are multiple points where you can stop. Okay, you can actually track down the recursive call and figure out, oh, so on line, okay, there's no line numbers here, so I can only 20. So this line of result equals to f of n minus 1 is going to call f again, and then we'll stop at the beginning of the conditional statement again. So you can track all of those things. And whenever the debugger pauses, you can use BT backtrace to look at the stack. You can look at all the call frames leading right to that particular moment. So in this case, we only get one single recursive call point, but in your program, there are two. So that means, you can actually tell, how did we get here? Okay, the first invocation, are we dealing with the first or the second call in the first invocation? Are we dealing with the first or the second call in the second invocation? And so on. So that gives you a much more complete picture of how recursive calls work when you have especially multiple recursion calls within the same function, which is the case in Fibonacci, but not so much in this case. So do we have any questions about how to convert something like this into something like this? And do we know how to do that to the Fibonacci program? Question?
So you're just elongating it.
I'm expressing the same logic, but allowing myself to have multiple statements. So this way, when I need to trace the execution of the program, it is easier to keep track of who calls whom with what as the parameter. We okay so far with that concept. Well, first of all, do you see how these two functions are functionally the same? Okay, so now when you think about your Fibonacci program, okay, your Fibonacci program looks very similar to the summation one, except instead of having n plus f of n minus 1, you have f of n minus 1 plus f of n minus 2, right? So it's not really that big of a difference. What is going to be different is when you look into the verbose code. So the verbose version is not going to have n equal to 0 because the condition is different in the Fibonacci program, right? But the most important part has to do with the else portion. This one says result gets f of n minus 1, and yours will also need result equals to plus equal to f of n minus 2. Okay, that is how you want to modify this code for the Fibonacci program, if this is how you want to get a better insight of how the recursive definition works. Any questions about that? Do we know how to convert the Fibonacci function f into something that looks like this? Okay, go through the same process, make it longer, make it more verbose, and make it easier to understand in C or C++. Okay, yes.
So after we run this program in TTP, the register A should have like the final answer of the Fibonacci of like anything.
In the code, in the one that you turn in, it would actually be stored in local variable x of main, which means location FF will have the return value of F. So you can check that. If you check, register A, it's not going to be easy because of the recursive nature. Register A will get updated at the end of each invocation, which means you will see multiple updates. If you're referring to the last time that you update register A, then it's the second last time that you update register A because main itself returns a 0. So you have to look back, to the second last time that you update register A. I think it's easier to track location FF because we store that return value into local variable x of main, which is living at location FF. I take it back, it's location FE because FF is the return address for main to return to the entry code. So it will be FE instead of FF. All right, so now assuming that we know how to convert a very terse but concise way of expressing Fibonacci into something that is longer, that gives you multiple places you can put a breakpoint so that you can fully understand how this code works in C and C++. Then it's time to convert it into TTP ASM, or the assembly code using my toy processor architecture. Is that okay? All right. Now, does that mean that I really need to go through this step before I can start coding in TTP ASM? The answer is no. Okay, because the way we call a subroutine does not change when it is recursive or not. So that means the whole thing about, oh, we need to push the argument, we need to push the return address, we continue execution at the called subroutine, and then we use register A as the return value, and then the caller is responsible to deallocate the argument. All those things do not change. Just because you're calling F from F does not change a single thing. All right. The fact, how we access the parameter n from inside the function also does not change. Okay, so in this case, n is right below, or excuse me, right above the return address. And at the entry point of the subroutine, the stack pointer points to the return address, which means parameter n is 1 byte past, 1 byte above where the stack pointer is pointing to. All right, and that's without using any local variables. If you do use local variables, like in this case, then you have to allocate and deallocate the local variables as we talked about, in last week's lecture. Is that okay? So the key point is, okay, do not let the recursive nature to throw you off, because the mechanism of calling, returning, pushing arguments, accessing the parameter, returning a value, none of those concepts is changed just because we're dealing with recursive calls. Are we doing okay? All right. All right. So when it's time to start the implementation, I would start with something simple. In other words, if the code looks like this, I would start with something that looks like this. You go like, what does that have anything to do with the homework assignment or the sample program in this case? I would say there's quite a few, right? You do need to make sure that you know how to access the parameter n. You need to know how to do the calculation with the parameter. And you also need to know how to return the value and also return the caller. If you can verify that this is working 100%, that gives you the confirmation that you know how to push the argument, you know how to get to the parameter, you know how to use the parameter for some calculation, and use that as a return value, and you know how to return back to the caller. I call that initial success, okay? Because you cannot proceed any further without these things already in place. So just implementing the program as this is going to be helpful already. It is not a waste of time. Because if you skip all the way and go like, oh, I can deal with the most complex forms of this particular program, you might end up spending a lot more time to debug, because you're debugging a lot more lines of code at the same time, as opposed to, oh, this is relatively simple. I'm just going to do this and see if that works. So once you get this to work, okay, which verifies that you can access a parameter, you know how to return the value, you can allocate a local variable, and you know how to assign a value to a local variable, like so, then you can move on to the next point. So the next one is going to have a conditional statement. In other words, this time, you're really just checking and adding additional code to say, can I deal with a conditional statement? So you want, in this case, you want to pass n as a 0 as one test case, in which case it returns a 1 in this case. And you want to try, let's say, 3 as a value of n, then it should return 45 as a result. So you might ask, so what does this program have anything to do with the program that I need to write? Well, I mean, at least you have the condition and the conditional statement. If this works, then you are basically adding on top of what was verified to be working before. You're adding on top of that, then you know how to implement a conditional statement. You know how to evaluate a condition in this case, which is not the same condition that you have to deal with. But nonetheless, you're double checking, and you know that the structure of your conditional statement is correct before you move on. Is that okay? All right. So let's just say that you got this version of the program working. Okay, then what should you do? Then you deal with one single recursive call. Okay, so in this case, I'm only dealing with calling f recursively with n minus one. So in this case, you kind of want to run the C code and know what it is supposed to return. So in this case, what do you think f of 20 is going to return? One. Exactly. F of 20, just like f of 19, just like f of 18, just like f of 17, and just like all the way down to f of 1, returns 1. Okay? But why do I want to test the program like this? Because now you're testing, if I do one recursive call in the function, does it work? Now, if it works, okay, even though it doesn't seem to be very meaningful by itself, but if this one works and always returns a value of 1, it doesn't corrupt the stack, everything seems to work, then it's good confirmation that you got the recursive call part done correctly. Okay? So we are adding one step at a time to the program that you're writing. So eventually, after this is working, then you can go all the way back to whatever the original form is. But you can see that, oh, so that's not too bad. I mean, this is just adding one more statement here. We are really just adding n to result in order to return it. So that would be the one last little piece for this particular example. In the Fibonacci program, it's a little bit more complex, but not much more, okay? Because you have two recursive calls. You want to separate the two recursive calls into two different statements. So this way, you can test the first one first. If that works, then you add the second recursive call and then add the return value of the second recursive call to result. Are we doing okay so far with this discussion? Yep. For the Fibonacci program? Well, let's take a look at the announcement itself, okay? Because the announcement itself actually mentions something about what you need to do specifically for your homework assignment. And I even spelled that out here. You have the first call, you put that result into the result, and then you have the second call where you add the return value of the second call to what is already in result. So I'm basically spelling out what you need to do to kind of incrementally write the Fibonacci program.
And then every time you call the FLN, you'll have to add the return address to the stack. Like at the bottom.
Okay, every time you call, you have to push the return address. It doesn't matter whether you're calling from main to F or from F to F or from whatever to whatever. Function call always involve pushing the return address as the last thing that you do before you do a JMPI with the subroutine. That is the caller callee agreement. And that doesn't change. Okay, the caller calling agreement does not change in any way when you're dealing with a recursive call. In other words, it doesn't matter that F is calling up, F is calling F, or it's calling G, or it's calling H. It's the same steps that you need to go through to call the subroutine. Is that okay? Does that help?
That is a clarifying.
Okay.
So then every time. I go to have a call. Load the recursive area. Then it's like, if you've already like done it once.
Each call is going to be involve the same kind of code.
Yeah.
Yep. Yep.
If we make it, like, do we write those back to back?
Hmm?
Do we write those back to back? Result equals F, n minus 1, then result equals result plus n.
F of n minus 2. What do you mean by back to back?
So is there anything between those two?
No, no, this is really just, okay, so what you do is you find out how to stick this into. Oh, did I just get rid of it? Nope. So, okay, this is good. So you want to determine where this goes within this code here. Okay, I hope you guys can do that. Because what I just mentioned had absolutely nothing to do with assembly language programming. That is just CISP 360 and CISP 300 material.
Are you asking us to think?
Hmm?
So were you asking us as to where it goes or?
I'm basically saying that I have already left behind the clues that is needed in order to turn this code to fit the Fibonacci code. So by combining this somehow into here and changing the condition here and changing what the non-recursive call is going to return, you have the Fibonacci version that is spelled out in a verbose way. But exactly how that is done, I'm not going to explain because that is something for you guys to figure out. Because it only involves understanding of conditional statements and how things are done using expressions. So I'm not going to explain it in the lecture, but if you're in the lab and you absolutely want me to kind of give you a clue, I can do that. It's just that, I'm not going to do it in the lecture. I want you guys to think about that. So are we clear what I want you guys to be able to do? Or to try to, at least you'll try to figure it out. Okay, all right. All right, so that's about all I have to disclose as far as clues of getting this program done. And then I also have this part here. To test the Fibonacci function, I recommend first testing it with f of 0 and f of 1, because those are the two test cases that are non-recursive. So if your program works for those two cases, then you have enough reason to test for f of 2. But if it doesn't work for any one of these two, debug it first, because it won't work with f of 2 if at least one of these two is not working. Is that okay? Does that make sense? Because of the recursive nature of function f. So after you test f of 0 and f of 1, I know as much as you're excited, you're like, oh, it has to be working. Let's try f of 8. Okay, no, try f of 2. Okay, don't skip numbers. If it works for f of 2, then you try f of 3, and then you try f of 4. By the time you get to f of 5, if that works, I think you can have pretty good confidence that it's going to work in general. But don't just try, oh, I'm going to start off with try f of 5. That would not be advisable. All right, and that sums it up, of all the extra material that I want to introduce to help you to get this program done. Oh, actually, there are a few more. Okay, I'm going to leave a few more little clues around. Do you guys remember Johnny as a function, Brian as a function, and then 12 as a function? There's a little trick in that program that you need to use here. Well, depends on the implementation, but you are returning the sum of two function calls in a single expression. That requires the use of that one little trick. So you might need to go back and review that particular program, which I think I shared with all of you through the announcements. If not, let me know and I'll reshare, but I'm pretty sure I shared those programs already. So that's one. And then the second one is also about the program that we did last week. What was the sample program that I did last week?
You did S0,
To this,
and then you did two tacky, compare those two.
Right.
String compare, yeah. So-
Yeah, I did a string compare, but I also did one where there are two parameters that you need to push.
The swap.
the pointers, you had like 67, 7 with the linked list, you put them all in the right
Yeah, that one, and also the swap subroutine. The call to the swap subroutine shows you one more thing that is important. It has to do with, you have to keep track of what is on the stack. The labels can only help you to go from where the stack pointer points to the thing that the label is trying to label, but only assuming that you did not push any additional items on the stack. So that means when you're pushing, when you already have some additional items on the stack, you need to adjust the offset from where the stack pointer points to the thing that you need to access on the stack. Okay, so that is one thing that you also might need to take into consideration, depending on whether you are using the really shorthand version like this one, or you're using the longhand version like this one here. If you're using the longhand version, you do not need to take into consideration of what I just said a little bit earlier, which is basically the sample program with Ryan and Johnny, and also, when we need to make adjustments to the displacement of things on the stack when you have already pushed additional items on the stack. So if you use the longhand version, which is in section 1.2, then you do not have to take those things into consideration. Does that mean you don't have to understand it and just go like, okay, I guess I don't have to know that anymore? The answer is absolutely not, because the final exam will definitely test whether you understand those concepts or not. So I would definitely make sure that we understand all of those concepts. So that means, each sample program that I gave you, give you an explanation of something that is important. So you need to write down, those key concepts with every single program, with every single line. There is something significant about all of those. Okay. How many people have actually looked at the program that we went through in class and used your own notes to add commenting so that you know which register is related to which construct in C in what way? Okay, I see a few hands. I'm gonna say that is important, okay? I'm just gonna say it is important. You don't have to do it to every single line because there are several lines, many lines that are repetitive. So as long as you understand the key concepts, it's like, yep, I got this. Oh, this is exactly the same thing. Don't comment, the additional things if they're exactly the same, but you need to understand, how the code works, okay? All right. Any other questions? If there are no questions, we have about 15 minutes or so, a little less than 50 minutes, to talk about a new programming assignment that is due next Thursday, which is our last day of lecture. It's our last lecture. So this one has a little bit more than a week for you guys to do it. And please do not procrastinate until next Wednesday, because it will be really difficult to get it done in one single day. And if you ask, but Tech, can you do that? I go like, yeah, I can do it. Doesn't mean that you can. It's just like, Shaq O'Neal, told his kids, I'm rich, you're not. So that means, start early and ask questions, okay? I don't mind, I'm not sharing my wealth, but I'm sharing what I know about programming, and I will be more than happy to help clarify concepts that you need to understand to get that program to work. All right, so having said that, we'll go ahead and take a look at the program that you are gonna, you will be writing and, for the next week or so. So that would be the starter for the lab today. It is a single zip file. Yep.
Is there a quiz done today, or is it just those?
There's a little quiz, I think it's like a 3-point quiz or something like that. It's kind of insignificant. But the program itself is quite significant. So I would definitely treat this particular, not so much the lab, but treat the programming part of this assignment seriously. Like allocate enough time for it. All right, so we'll go ahead and take a look at the code, which is here, okay? So we're gonna look at the C code first, just, as usual. You look at the C code. And we have a node, struct node definition. This is a struct definition. There are three members to a struct node. The first one is called value. It is an unsigned 8-bit integer. And the other two are pointers to struct nodes. So that means, hey, we have seen something like this already, okay? Because last week we talked about the linked list, where there's only one member that is a pointer to the same kind of structure. This time there are two of them. Okay, so it's not a really big stretch of what we did from last week. Function traverse from line 9 to line 17 is what you need to implement. The main program is already done. So what you need to implement is from line 9 to line 17. So we'll get back to talk about traverse in just a little bit. I just want to give you the context of the entire program first. So then we move on and we take a look at main. And that's the entire main. You look at this main here, and it does resemble a little bit of the linked list sample program that we talked about last week. It has static local variables, N1 to N5 this time. Just a few more, and the way they are initialized is very similar to what we did last week with the linked list program. We have a local variable R that is not static. And we also have a local variable A pointer or array pointer that is also not static. So those two are dynamic, they're on the stack. So up to line 29, do we have any questions? Because up to line 29, I think this should have enough resemblance to the linked list program that we talked about last week. That is like, okay, we've got some additional stuff, but not much more. Are we good so far? Right, okay. So line 33 is a call to traverse. And so now we have to think about how do we push those two arguments on the stack. So the two arguments, one is the address of N1, which is a static, and the other one is the address of APTR, which is all. So one lives on the stack, the other one does not. So you don't really have to worry too much about this because I'm giving you the assembly code of the entire main. So this part is done already. And the main returns a 0. So the main function itself is not really that significant, okay? Because it's all done for you for one thing, and two, all it really is trying to do is to set up the data structures and then call the subroutine to have the subroutine to do all the actual work. Okay, so the key is not so much main, it is in the subroutine traverse. So now we go back and we take a look at traverse, and we'll look at this one line by line. Okay, we'll make sure that we understand the C code. So on line 9, it is the prototype of traverse. It has two parameters. It has PTR as a pointer to a struct node, and then it has array as a double pointer to an unsigned int. What does that mean when we have a double pointer, when we have two asterisks? The parameter is a pointer to an unsigned 8-bit unsigned integer. Is that okay? Do we have any questions about that concept? It's a pointer to an integer. So that means if you want to get to the integer, what do you need to do? Follow the pointer once to get to a pointer to the integer, follow that once to get to the actual integer. Does that make sense? Okay. So what do we do next? Well, the next thing we do is we get into the function. On line 11, the condition is PTR. Do we all understand what that means? When the pointer is not a null. Yep. In other words, it is the same thing as this. But we can shortcut it because C and C++ does allow you to do this. Not so much in Java. Yes?
So when you pass something into that function, the second part is just an integer?
The second part, you mean array?
Yeah, the double, so is it? So
You're passing an address of a pointer to an integer as array.
So, okay.
All right, okay, so are we good with that one? Okay. So are we good with line 11 as well? You know, what we are checking? Can you already start to visualize the code to do that? Because this is not the first time we have to check whether something is a 0 or not. We have done that many times already, okay? So, you know, hopefully you remember how to do this, you know, what instruction to use and what conditional branch to use and in what structure do we use that. And the good thing about this conditional statement is it doesn't have an else. Okay, you know, the else is basically just an empty statement. So if the pointer is null, we simply have nothing to do. We just say, oh, okay, time to reach out right away.
Instead of finding those pointers for arrays, so you can increment it. Because otherwise.
Well, we get to that. When we get to that, we'll talk about it. We're not quite there yet. Okay, I'm going line by line. So we go with line 11, the condition of the conditional statement. Okay. So now we get to line 13. Line 13 is a recursive call to traverse. So we'll take a look at the arguments. What are we pushing on the stack? The first argument is PTR points to L. What is that? Okay, so the way to describe it is member L of the structure that is pointed to by PTR. How do we get that? Okay, so that's a question that you kind of need to figure out. And then the second one is really just array. Okay, in other words, whatever array is as a parameter to you, just pass it along. You don't have to take the address off. You don't have to dereference whatsoever. Whatever array is passed to you as a subroutine, you just pass it along to the recursive call. So are we good with line 13? What it needs to do? Yes, no, maybe. Okay. How about line 14? Line 14 is the nasty one, right? So what I'll do is I'm going to do something that makes it a little bit easier to read by doing the post increment in a subsequent instruction. So we are, oh, okay. So we're going to get rid of the double, the post increment, and then over here we do the actual increment here. There we go. Okay. So this code is identical functionally to the code before, except this time we don't have to deal with the post increment operator. We just say, okay, we'll just deal with one thing at a time. Line 14 is one thing, and then line 15 is a separate thing. That makes it a little bit easier, okay, to really look at and make sure that we get the right thing done. All right, so we'll start with line 14, the right-hand side of the assignment. It is the value member of the structure that PTR points to. Okay. Do we know how to get to that? Or if you cannot remember, because okay, there are a lot of things happening, I'm taking a lot of classes, I cannot remember exactly how to do it. Do you remember where to look up to find out how to do that? We talked about that last Thursday. Okay, so if you look at the linked list program, it will give you some idea of how to access a member of a structure that a pointer points to. So the right-hand side is easy. The left-hand side is basically just dereferencing array twice, because in this case, because I'm not doing the post increment here, that means the parentheses are really unnecessary because we are just dereferencing and then dereferencing again. Okay, so the first thing you need to do is to get to array, which is just a parameter. Then you dereference it once, and then you store to what that thing points to. So if you know how to dereference once, you already know how to dereference twice. Are we doing okay with that one? Now, when I show you how this code works, like line by line, step by step, I think that will help you understand it as well. Yep.
Okay, so the array is not actually an array, it's a integer.
It is best described as a pointer to an unsigned APT.
Where does it really point?
It points to a local variable that main has. So array is actually going to store the address of APTR of main. because of the way we pass that to traverse. It'll be clear when I run this code, okay? So just bear with me a little bit longer, because when I run this code, you guys will start to visualize and be able to see what is happening. So that's line 14, and then line 15 is kind of going like, okay, we don't want to increment array, but we want to increment what array points to. Okay. So that is something that the swap subroutine also do. Okay, well, not the incrementing part, but getting to what a pointer points to is what the swap subroutine also had to do. So we already have some fragments of code that relates to line 15 already. Line 16 is basically the same thing as line 13, except we're using member R instead of member L. So if you know how to do line 13, you already know how to do line 16. All right. So one more thing before we switch to using GDB to kind of get an idea of how this code works. Okay, one more thing is when you implement this program, the first thing you want to do is not to implement everything at the same time. So you don't want to implement line 13, 14, 15, and 16 all at the same time. I would just do line 13. Just comment out the rest and make sure that you can do that one. Now, if you ask, but I have no idea what is the correct behavior in that case. Easy peasy. Comment out the C code, run the C code, find out what it does, and then you would expect the same thing to happen in the assembly code. Okay, so if that is working, then you want to add line 14 and then figure out what the C code is doing, and then you want to add line 15, and then finally, if those are all working, then you add line 16. The nice thing, one resource that you have in this case is the C code is given to you already. So you can use GDB to help you understand what the code is supposed to do, and use that as a reference when you're debugging the assembly code. All right. One more thing, is when you are debugging the program, you can also change, the first parameter here. Using N1 as a starting point is the most difficult case of testing this program. So I wouldn't do that as the first step. I would use N4 or N5 to start with. So in that case, because they do not have a R or an L member, well, they're both zeros. So that means, they would do the least amount of recursion. So I would test that first. If you want it to be even simpler, pass a 0. Okay, change the first argument to traverse from line 34 to a 0. That should basically just go into the subroutine, check whether PTR is 0 or not. It is 0, return right away without doing a single thing. So that would be the first test case of this entire program, is to use a 0 as the first argument to traverse on line 34. If that is successful, then use N4 or N5 as the first argument, or the address of N4 or N5 as the first argument. If that is also successful, then you can use N3 or N2. And if that is also successful, then use N1. So there is a certain progression of what to use to test whether your code is working or not. Are we doing okay so far? I know I'm talking kind of fast, but you might want to kind of review the video and then just jot down the process of how to test and implement the program gradually and not try to get everything done all at the same time. Are we good so far? Okay, so now we're going to go in and actually try to run this code. So gcc-g-o tree.c GDB tree. Okay, so now the question is, how do we use the debugger to help us understand what is going on? Well, I'm going to look at the main program, okay? And I will put a breakpoint on the very first line that does something useful, which is on line 32. Run the code. Okay, so now this is right before the assignment. I want to know what is R, okay? So it tells me what R is. R is an array of 5 unsigned 8-bit integers, and these are all in R. Okay? It's uninitialized. Okay, so that means well, whatever it is, okay, it doesn't really matter. When we do a single step, okay, single step, And then we want to find out what is in APTR as a local variable of main. So APTR has a value of, this thing here. You go like, hey, that looks a little bit like this. Okay, you look at these two things. Well, that's because of the way we initialize APTR. APTR becomes, it points to the beginning of the array. Are we doing okay so far with this? Now, this code is already provided to you. So if you open tree.tpp.asm, this code is already done. I would definitely strongly suggest you to read that code as well and possibly trace through the execution so that you know what is in each variable and where they are on the stack, okay? Because that will come in important later on. So now we do the first call to traverse from main, and I'm going to single step, okay? We're single stepping into it. So this is the first call to traverse, and GDB is really nice because it tells you what PTR is. PTR is an address of a struct node. Which struct node are we talking about? It is struct node N1 of main. Okay, so that is really helpful. And what is array? If you look at this thing here, go like, that is not the same thing as this one here. Because APTR has a value that ends with BD, but array as a parameter to traverse ends with B0. It's like, what is going on here? So what we want to do is go like, oh, one thing we did not do is to try to look at the address of local variable APTR of main. And you're thinking, it's too late already. TAC will do this all over again so we can check the address of APTR. You don't have to do that. We don't have to run the program all over again. Why not? We talked about two features of GDB that will allow us to figure out what is the address of APTR of main, even when we are now in a function that main is called. How do we do that? Backtrace is one, and then frame is the other one, okay? So we first use backtrace BT. It shows us that frame 0 is where we are at this point. We are in traverse right now. Frame 1 is in main. So now we say frame 1, which means we change our context back to the caller. We are not returning, okay? The debugger is still stopped or paused in traverse. We are only changing the perspective of the debugger. Which context am I using? Am I using the context of the last invocation of traverse, or am I using the context of the caller of traverse, which is main? So I just switched the context to main, which means all the local variable of main is now available to GDB for me to examine. So now we can say print the address of APTR. You go like, oh, so that's what array is, because the address of APTR is parameter array of traverse. So that is what it is. Array as a parameter is basically the address of APTR of main. So immediately there's a question, which is, why do we have to use a double pointer? Can the single pointer do the whole thing? Well, the thing is, we want to change, okay? We want traverse to be able to change APTR of main. And that's why we are passing the address of APTR as array of traverse, because traverse needs to change it. Is that okay so far? Okay. All right, so now we go back to frame 0 so that we can continue the execution of the program. So what is PTR? It is definitely not null. So that means we're getting into the then statement of the conditional statement, so single step. And now we're going to call again. So now when we call again, we're going to ask, so when we call this one, what is going to be the first argument? Well, we can always examine what PTR is pointing. So we can say, what is PTR pointing to? PTR is pointing to a struct node. That particular struct node has the value member B5. It has the L member being this thing. And GDB is very nice. It tells you that, oh, the L member of the structure pointed to by PTR is really just the address of N2. And it's telling you that R as a member of the structure, the PTR is pointing to, is really just, it's the address of N. Are we still doing okay so far with this code? And how you can basically examine, what is going on when you execute the C code. Yes, questions? Okay, so I don't see any questions. All right, so we'll single step, okay, single step. So this is the second invocation of traverse. How do I know? Well, we can always use backtrace. So backtrace tells us that we are currently on line 11 of this program. We got here because we called on line 13 of the same program, and we got there because we called traverse the first time for main on line 34. So backtrace is very helpful to tell you exactly how you got to the point where you are, when you have paused at this point. Okay, so now we take a look at PTR. PTR is definitely not null, which means we go into the conditional statement again, or the then portion, and now we're going to call again. So this time we're going to look at whatever PTR points to, and this time the L member, which is left, is a 0, it's a null pointer. Are we going to call? Yeah, we're still going to call, because we are already at this point. This part is not conditional. We are going to call traverse. We're going to call traverse with a null pointer or a 0 as our first argument. Are we still doing okay so far with this? Okay, so we'll go ahead and single step. And this is, yet another invocation of traverse. Now, if you just say, okay, I'm losing track of, how many times we have done this recursive call, no big deal. BT will show you. So we are at the third invocation of traverse. The first call to traverse uses the address of N1. The second call to traverse uses the address of N2 as PTR. And then the last call, which is where we are now, is using null as PTR. Okay. Do we have any questions about how we are getting through this entire program up to this point? No questions? All right, so we got a single step, okay? What do you think is going to do, the program is going to do if I single step? We are currently on line 11. It's checking whether PTR is null or not, which it really is, or I should say whether it's non-null or not, and PTR is null. So what do you think it's going to do next? Just describe it. It skips over the entire conditional statement, right? Okay, and it gets to the end of traverse, and it's going to return. Where does it return to? I think it's going to return to the next line, right? Because this is how we got here. So when this returns, we're going to continue of traverse past line 13. Does that make sense? Okay, so now we get to that line, single step, and sure enough, we are now on line 14 of traverse, and this is what it needs to do. And we have the right-hand side and the left-hand side of an assignment. So we want to first figure out what is going to be on the right-hand side. Okay, so the right-hand side is basically asking what is the value member of N2? That's basically what it's asking. But you can always just print it out like so, and the value is supposed to be 3. So the right-hand side of the assignment on line 14 is supposed to be 3. But where are we going to store that to? What is the left-hand side? It looks kind of funky with 2 asterisks. We have never seen anything like that. But the thing is, if you have seen one single asterisk, you know what it does. Then what does it matter that you have multiple asterisks? Because it's the same operation that you're performing, you're dereferencing. So the way we want to do this is kind of do it step by step. We want to figure out what is array first. Array, you know what it is, okay? So can someone remind me what is array? We figure out, yeah.
Like the first, isn't it like the first value of the array, like the point of
Not, okay, so I think you're getting a little bit ahead, okay? I know why you said that, but that's not what array is. So array is what? Okay, so let's go ahead and do a BT. Huh? It is, okay, so what you described is close to what it is, but it is not precisely what you just described. So I'm going to show you what it is, okay? So we're gonna do BT. Main is now frame 2, so we go to frame 2. And then we say, tell me, where is APTR? Oh, so that is what array is. Because when you look at array from before we change the frame, this is what array is, okay? It is basically the address of APTR. Is that okay? In other words, all these calls, all these recursive calls, they are really just passing quote unquote array as a parameter to the next invocation, so that every single invocation of traverse knows where to find APTR of main. Is that statement okay? Is that statement understood? Also, do you understand why what I just said is close to, but not exactly what you said a little bit earlier? Because you said that array is APTR of main. Close. Because array is the address of APTR of main. That address of is important. Are we doing okay so far? I know it looks kind of convoluted at this point. Are we good? Yes? Okay.
So when we're using the double trace.
Yep.
Value, that's what APTR points to, right? Because it's.
What, that is correct. Yep, that is correct. But let me explain that one step at a time, okay? So if I ask, okay, print array, it is the address of APTR of main. That's what you're seeing right now. If I ask one dereference of that, that is the value of APTR of main, which is currently pointing to, how did we initialize APTR of main? It points to the beginning of the array of main, right? So that's what it is, okay? So now one dereference of array as a parameter to traverse get us to the value of APTR, which at this point is pointing to the beginning of the entire, the 5-character array of main. We good so far? But it is just a pointer. We don't want to overwrite the pointer itself. We want to overwrite what it points to. So when we get to double asterisk array, this is what is at the location that we are about to overwrite. We good? So we are using a value of 3, which is on the right-hand side, to overwrite the first character of the array that is in main. Is that okay? All right. So now we single step and go like, okay, so that should have happened. How do I double check? Well, you can say, well, we can always just do another print double asterisk array, and it is a 3. The update was successful. Are we really sure that we updated the first character of the array as a local variable of main? Not at this point. Yes.
So when we do that, the increment, the array, are we updating the address of APTR?
No, we are updating APTR so that it points to the next available location in the array.
APTR itself.
APTR itself is updated. Yep. But at this point, so you're one step ahead, which is great. But let's get back to this one and double check that we actually did update the first element of the local variable array in main. So how do we do that? Okay, I have a strong suspicion this is what we just did, but we are in traverse right now, which has no visibility of the local variables of main. So what do we do? Backtrace first, figure out which frame is the one we want to go to. It would appear that frame 2 is the one that we need to go to. So we go back to frame 2. And then once we get here, we can take a look at, so R is the name of the local variable. So now we want to say, okay, now from the perspective of main, what is the first element of the local variable var R? And it is 3. So this is a verification that yes, we just updated the first element of R of main using APTR, which is also a local variable of main to get to it. And there was a hand earlier. Nope. Is that okay so far? All right. All right, so if this is okay, we go back to frame 0 so that we can continue, tracking down this program. So the next statement that we need to do is adding 1 to whatever array as a parameter is pointing to. Remind me again, what is array itself? No. No, array is the address of APTR of main, which in return is currently pointing to the first element of local variable var R of main. So array itself is the address of APTR. So what is the dereference of array? It'll just be APTR. So we are basically just adding 1 to APTR of main. So that it advances the pointer to get to the next available location of local variable R of main.
Array in traverse.
Huh?
You asked array is
Yeah.
in traverse.
Say that one more time.
You said you asked, oh, what is array?
Yes.
But you asked, what is array
What is array
in the
in traverse? That is correct.
what is array, just like in the whole. Never mind.
Okay, array is the name of the parameter of traverse. The local variable in main is called R, ARR. Yeah, so there's only one array in the entire program, which is the parameter array of traverse. Yep, go ahead.
Array or like the address of APTR, that doesn't change.
That doesn't change.
APTR itself changes, right?
That is correct. So what do we want to do? We want to double check that is the case, right? So one thing is we're going to go back to frame 2 again, which is main, and say, what is APTR pointing to? APTR is pointing to the location that ends with BB. So now we change the frame back to 0, and then we single step, okay? Which means if the theory was right, okay, if array is indeed the address of APTR of main, after this step, APTR should now be pointing to blah, 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 FB. Is that correct? Because array is the address of APTR, we just updated whatever array points to, which means we just updated APTR of main to be 1 more than what it used to be. It used to have a value of blah, 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 BB. You just incremented it. So that means it should be blah, 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 BC at this point. Okay, so we'll double check. Okay, so we go back to main, frame 2, okay, and we say, tell me what is APTR of main. Ah, okay, so it is incremented to PBC at this point. So that confirms what we are actually changing. We are not changing what APTR points to, we're changing APTR itself when we're dealing with line 15 of traverse. We still good so far? You guys still with me? All right. So now we go back to frame 0, and then we single step. So we are now ready to call traverse again, and this time using the R member. So we want to say, is there anything there? Yep. R has R is a pointer, it points to N4. Okay, so when we single step, this time, the PTR is non-null. So we get into the subroutine and then we ask, what about this particular PTR? What does it point to? Well, both member L and member R are null. So that means this entire call is not going to do anything because we tried this already. When we pass a null pointer as the first argument, the subroutine call simply does not do a single thing. So that means we really do not need to single step through this one. So if you don't want to single step through a function call, you can use and or next. So next is going to execute the function call, but it's not going to stop at the entry point of the subroutine. So that can save you a little bit of time if you say, we don't need to trace this one all the way down. So you use and for next. So now we update whatever array we update the byte that is pointed to by the pointer that in return is pointed to by array, which is what? Which location am I going to update? From the perspective of R as an array in main, which element are we updating now? Element 1, the second one. Okay, very good. So the question is, what are we going to update it with? Well, that kind of depends on what is pointer pointing to. And it points to a structure that has a value of 4. So we are updating R as an array in main, and the second element is now updated to a value of 4. So we single step, and I'm not going to go back to main just yet. I'm going to finish this one too. So now we go through the same code again, which is we are adding 1 to whatever array is pointing to. Array is the address of APTR of main. So once we dereference it, it becomes APTR of main. So we are incrementing the pointer APTR of main itself. Okay, so we'll single step this one too. And this would be a good time to go back to main and go like, okay, did we just correctly mess around with your step? Okay, so we do a BT. And the frame is now number 3 because it is 3 frames away from where we are. And that's how the frame numbers are determined. So frame 3, and we say, okay, APTR, where are you pointing to? Oh, it's pointing to BD. Okay, that's kind of what we expected. And then we also want to say, what about R? Okay, as an array, what do you have? I have 3 as my first element, I have 4 as my second element. And then what we expect. Okay. So that's how you kind of track down this program step by step to understand how the C code works. So once again, if I continue this program the execution of this program and go all the way to line 35, what you should see in R to look like this. You go like, what is that? I know the first 3 are numbers. We got 3, 4, and 5. What is \T? \T is the tab character, which I think has an ASCII code of 9. And then \N is the new line character, which has an ASCII code of 10. So basically, you're looking at an array with the values of 3, 4, 5, 9, and 10. So are we doing okay with these arrays? Yep.
Why is it a value of 10? That's just what it is in the ASCII table.
So so there are 2 layers to that question. Why is it 10? It is 10 because 10 is the value of one of the nodes that the last one that you actually traverse. But the second level of the answer to that question is line feed has an ASCII code of 10.
Okay.
And line feed appears as \N, and I hope you guys talked about that in CISP310 as well, is the escape code of the line feed character is \N if you put it into a double quoted string. Are we still doing okay so far with this code? So once again, okay, let me look at the time. We have 7 minutes. So how do you get started with this program? Okay, let me go all the way back out. Okay. So how do you get started with this C code here. Oh, okay, that's not the command I was thinking of. So how do we get started with this program here? Well, let me do this, B split. And then we look at tree.ttp ASM. So how do we get started? First thing is to understand the assembly code, okay? This is the usual entry code, starting with a no op so that we can use the command line way of tracing, which I'm hoping you guys already understand how to do, because I think in this program, it is particularly helpful. And then we have traverse, and this is what you need to do. You need to define this particular subroutine. Main is done for you already. So as far as main is concerned, we have a local variable var that takes up 5 bytes. We have local variable APTR that takes up 1 byte. So together, we are using 6 bytes on the stack for all of the local variables. And several people ask me, what is LVS? It is local variable size. Okay, LVS stands for local variable size. So this is a useful label because I need to remember to allocate that many bytes from the stack for my local variables. And when everything is said and done, I also need to deallocate the same number of bytes on the stack so that I can get back to the return address. And then inside the subroutine itself, inside main, this is the assignment statement. So let me go back to the C code. So line 32 of the C code corresponds to line 40 to line 45. So we'll double check that code and make sure that we understand it. Okay, this is basically another review of how to get to things on the stack. Line 40 is going to load the offset of R to register A. When I said offset, it is an offset from where the stack pointer points to. So when you add the stack pointer to the offset, it becomes the address of R. So now we have the address of R in register A. Line 42 and line 43 combined is going to compute the address of APTR. So that on line 44, we basically just say store the address of R to local variable APTR. That's what line 44 is going to finish up doing, which is corresponding to line 32 of the C code. We good so far? Okay. And then we move on to your code. Okay, so I'm going to give you the call to. Okay, I forgot to. I was originally, trying to get you guys to write this code, but I'll give you this. It's a freebie. So we'll go ahead and I'm going to repack the whole thing and send you guys another announcement with this already done. All right, so does anyone want to help me to get this done? What do we need to do first? Line 34 of main. What do we need to do first? Not yet. Parameters, and I got 2 parameters. Which one do I deal with first? Second one, very good. So the second one, and what exactly is it? The address of APTR. Okay, very good. So how do we compute the address of APTR? If you're thinking, Tech, that's boring. We got it already. Yes.
Offset and then plus E.
How about we just do this? Because we already have it in register B, and we didn't do anything to clobber the value of register B after it has the address of APTR computed in it. So we can just reuse it. Okay. Then what do we need to do? We got the second argument pushed. What do we need to do next? We have to push the first argument, okay, which is the address of N1. And how do we do that? This is a trick question because N1 is not an auto local variable. It is a static. So how do we get the address of N1 in this case? This is something that we did last week. It's just the label itself, okay? It is just the label itself. So that means if I do a LDIA with main underscore N1, I got the address already because it is not on the stack. If it's not on the stack, why would I need to add the stack pointer to it first? Because it's not on it, okay? So this is it, and I just need to push it on the stack. So we do this. We got both arguments pushed. And then what do we need to do? Return address, okay? LDIA with .6+, because the return address is 6 bytes after the address of the LDI opcode itself. Decrement D, STDA, JMPI to the subroutine, which is traverse. And when it comes back, do we have anything else to do for the call to traverse? What is on the stack right now?
Parameters in the return.
The return address is not on the stack anymore, because if I get back to line 55 or whatever opcode is corresponding to line 55, the subroutine would have popped the return address already.
Or local variable.
Yes, those are still on the stack, but what is immediately on the stack right now? Not the return address. Return address is taken care of by the old subroutine as per the caller callee agreement. What else is on the stack? The parameter, the arguments. The arguments that we push are still on the stack. So what we did on line 46 to line 50, those 2 bytes are still sitting on the stack. Do I have any use of those 2 bytes at this point? The function is done. I don't need those anymore. So I just need to deallocate. I don't need to pop them per se. I just need them to be gone. So that means I need to increment the stack pointer twice in order to get rid of the 2 arguments. And now we are actually done with line 34. So that means from line 46 to line 56 is they're implementing line 34 of the C code. All right. So once again, when you are debugging or when you want to kind of write this code, kind of in a gradual way, the first thing you do is to change this N1 to N4 or N5. Or better yet, do this. Okay. So what happens when you do this? It wouldn't do anything, right? The subroutine traverse will look at the first parameter and it's going to say, oh, it's a null thing. And the only statement in traverse is a conditional statement, conditional to PTR. So if this is how we change the program, then nothing is going to change. R remains uninitialized. APTR remains exactly the same thing as it used to be. Program should terminate with no problem whatsoever. Would that be a worthwhile test case? Yes, this will be a worthwhile test case because if this does not work, you got work to do before you can implement any additional code in Traverse. So get this done first. The next test case, I know we are going a little bit over time, but the labs portion of today's class is going to be simple. So I'm going to use a little bit of time here. The next test case is to use N4 or N5. Why? Because N4 and N5 do not, they both have nulls for the left as well as the right members in the structure, which means they do call recursively. Okay, they will call one more time recursively, but the recursive calls will not have done a single thing. How many bytes are we going to use up in R of main if we change, line 48 of the assembly code, we use N4? It's going to use up 1 byte only. And the APTR of main would advance by only 1 location as well. So that would be the next test case, okay? So other than 0, change line 48 to use main underscore N4 or N5. If that works, what do you do next? You move on to either N2 or N3, because these two only has either the left-hand side or the right-hand side being non-null. So this way you can test just one of the 2 calls. Okay. If that works, then you move it back to N1. So that means, just from the perspective of main, there are multiple options for you to test your code in steps. All right, so are we feeling a little bit okay with this code? This is due next Thursday, which means, I can further explain, how to maybe get certain things done in this code or use some other additional sample program to illustrate the points and then let you guys make the connections. So, try to get this started before Thursday. So this way, on Thursday, you can ask specific questions and I'll try to come up with sample programs that are not a part of your homework assignment to illustrate the point that you need to understand. Okay, but if you don't do that part, I wouldn't know what I need to explain because, to me, this is all clear. And of course, it is, to me, it's all clear because if it is not clear to me, we have a big problem. The question is it clear to you? But you won't know until you give it a try. So that's what I want you guys to do is to give it a try, just to try to conceptualize the whole thing and give it the, like the initial trial so that you can come back with questions, hopefully on Thursday. All right, I'll give you the access code of the lab because there is a lab. It's not significant in any way, but there's one. So let me give you the code first. I should remember these things, but I cannot. So I think it is pointers and structures, and I have to change the time as well. So I got a few things I need to do, but you only need to know what is the access code. Nope, it does not require an access code. So you guys are good to go. I just need to set the time of this portion. Yep. Okay.
What did you add an access code for the other?
I think with this one, I did not set up an access code because, in previous semesters, I had to make this one do the same time as the program itself. But I want you guys to at least get this done tonight. So I want to kind of emphasize it.
All right.
Yep. And it'll be a good idea to get started with either program in the lab. So I can, if you guys have questions, I can stop by and